Is this thing on? I guess it is. Hello again, everybody. Hanging in there? Home stretch. All right, so actually, this is the first time we've met, so I got some new faces up here. So once again, I'm Mac from Fhenix, Content, Comms, and Marketing. Follow us on Twitter for the dank memes. How about you, sir? Let's hear from you first. Who are you, and where do you work?
Hi, I'm Tony. I'm a hardware engineer from Ingonyama. Actually, I'm a little bit, feel a little bit out of place here because as a hardware engineer, we usually live in the basement. But hopefully, you know, I can offer something of value here.
All right. Hi, everyone. My name is Zheng Leong. I'm the co-founder of Automata Network. So just a little bit about Automata Network. We strive to bring machine trust onto the entire Web3 ecosystem. So what we are kind of like working with is like trusted execution environments and kind of like the entire tech stack surrounding TEs or trusted execution environments. So I'm really happy to be here to discuss with like really technical people about like how can we actually kind of like combine all these different security gadgets that we have, and then how do we make the sum of all the parts? How do we make this the sum of all the parts greater than its sum? So yeah.
Yeah. Hi everyone. My name is Dennis, and I am the co-founder and chief security officer of My Network. With My Network, we are building FHE in Web3 world. Yeah, that's what we do.
Awesome. So we got ZK hardware, T, and FHE.
Yeah.
Awesome. So yeah, this is going to be pretty casual, but you know, common ground here, obviously, around encryption. Tony, I want to start with you, and I disagree that you don't belong here, sir. I think you definitely belong here. And I'm super interested to hear about hardware, because it's something maybe we don't hear about as much. So what are you excited about right now? Like, what are you guys working on? Where does ZK hardware currently stand?
Okay, let me just start off with what Ingonyama is. So we're a cryptography acceleration company. So we currently are focusing on accelerating ZKP, but we also have investigated FHE and MPC. So we kind of do quite a lot of things, but our primary focus right now is ZKP, and we currently, I think the most promising avenue is to onboard everyone onto from like their laptops and their CPU servers onto GPUs first. So GPUs, if you don't know, is
Graphical processing units?
exactly, yes. So they're typically used for gaming and recently for AI, and we've discovered that it's works extremely well for ZKP and also for FHE as well. So we create a library called Icicle that basically provides a whole bunch of cryptographic primitives like hash functions, like polynomial manipulation, stuff like MSM, NTT, FFT, and we're also about to release support for some check as well, which is used for many like modern ZKP proof systems. Yeah, I think GPUs are especially interesting because they're actually quite ubiquitous. So you have discrete, so-called discrete GPUs, which are basically if you're into gaming, you buy a gaming computer and you will have a dedicated card that you can plug into a.
And that's why they're ubiquitous, right? Because they're used for these other popular purposes.
Billions of gamers out there,
Yeah.
and they're actually quite cheap because of the economy of scale. Like the margins on gaming GPUs is actually quite low, so you're actually getting it at a very good deal. So we repurpose that for cryptography.
Smart.
Yeah, and also we're seeing a similar thing with AI. So right now, because AI is very hot and it's very computationally intensive, they're making specialized GPUs, so-called like big iron
Clusters.
Yeah, exactly. For AI, and I think right now the cost is quite high. I think I saw Automata do something with the H100 with
Yep.
the TEs. Yeah. So now the GPUs have TE inside. Right now the cost is quite high, but I think it will come down over time as, you know, the AI stuff start trickling down to us normal people. So we also have a hardware team, right? That's also where I'm at. So that's for we can also create custom hardware for cryptography as well.
Yeah, I want to ask you about this interplay between software and hardware, because it seems to me like clearly you need both. There's like a symbiotic relationship there. My sort of mental model or my understanding is that software often leads, like there's a lower barrier of entry, and then the hardware sort of comes in behind and fills in the gaps. Is that accurate? Is that an accurate statement?
So actually what we need to develop hardware is we need kind of, right now everything is kind of bubbly. So we have like new protocols and new proof system, new ideas every day, basically, it seems like. And you know, the timeline for hardware development is something like 6 months, a year, or years.
Can't move quite as fast.
Yeah. So we need like a standard before we can move that there.
Well, and that brings me to my next question, which I think you did touch on it, which is this hardware is applicable to other forms of encryption, like FHE, like sounds like TE's already been integrated.
Yep. So just to kind of like put it into perspective, like 6 months to a year is considered like blazing fast for hardware development work. It typically stretches like 4 or 5 years, like at least, and then you have to tape out, spend a lot of money, and then like take a look at it and realize that, oops, there's a bug, and then you have to go fix it again. It's a very painful thing. I'm glad I'm doing like a little bit more on the software side. So the thing about TE and like, you know, kind of like accelerator hardware for both like, I'll kind of like term it like cryptographic accelerators, basically. Can I put in a request with you?
Okay.
Maybe you can kind of like embed like a key, or kind of like find a way that allow users to do like key distribution onto the actual hardware itself, because that will actually allow us to kind of like attest the hardware that is actually producing the proofs, in this case, the ZK proof. And if you think about it, a lot of people think about TE as some magic thing or some magic bullet, panacea or something like that. But TE actually uses cryptography. So the kind of like the fundamental idea behind a trusted execution environment is isolation, like isolation of the computation environment from outside world. I can take a normal computer and shoot it up into space and no one can touch it, and I can use purely software methods to actually build the TE out of it. If I want my hardware on Earth, then I need to find another way to isolate it, right? And what better is it than to use cryptography, because math. So actually, if you think about it, TEs are actually an application of like math or cryptography. So kind of like bring back a little bit on like on like how can TEs work with like all the different kinds of cryptographic gadgets that we have. One, like in general, if you think about it, TEs can be an additive force to whatever gadgets that you are trying to do. For example, let's say I'm interested in generating a ZK proof. In order for me to have private ZK proof, the client themselves have to generate the proof, because I can actually see the inputs to the circuit, including the private inputs. But then, like, if most users are mobile users, I'm pretty sure about it. Like, all of us have a phone in our pocket. A raise of hands. Who here has an iPhone or an Android phone? Everyone. And you know what? All of you have a TE in your pocket. If we want to generate like those kind of complex ZK proofs from our phone, it's not feasible. there's too much computation that has to be done. What we can do is we can create a trusted execution environment that has like ZK accelerators, FHE accelerators on it, and then we perform the computation on it. The user can then put their private data into this trusted execution environment, and the hard work can be done on the server. And you know what? Apple has done it. The private cloud that Apple has been kind of like showing off for iOS 16, that is essentially that. A trusted execution environment with access to huge amount of computation power where the user can actually trust. It's like an extension of the user.
Yeah, so what I'm hearing you say, Zing, is that all these pets, all these privacy-enhancing technologies, they're in fact complementary to each other, right?
Yes.
And maybe it's just like a human error, like too often we like to do, this or, it's this versus this. I don't know, it's just like human nature to kind of like compare one thing to another. But these all work hand in hand. And like if you can't do just T, right? Because then the trust assumption is on the silicon and you didn't make it, so.
Yes, so the thing is like, if you ask me personally, I'm of the camp that believe that TEs can be broken and will be broken. Like, there's no doubt about that. But what if we combine TEs with like MPC? Or like, for example, for FHE networks, right? Typically, there's a need for us to have this decryption key, right? This threshold decryption mechanism. Most of the time, we use like threshold cryptography or like kind of like standardized MPC. Now, the thing is, with that, we have collusion risk. Put a TE there, and you get the best of both worlds. You get MPC, and then you get anti-collusion from the TE. So, yeah.
Positive sum, yeah. It's going to take all of these technologies working together to provide a real secure solution.
Exactly.
Dennis, we haven't heard much from you on the end there. Anything to add?
Yeah, I would introduce something about how we using FHE to empower the AI and POS network. Yeah, actually, compared with ZK and the TE, FHE is in a relatively early stage. Actually, we start to build it even earlier. We started it 2.5 years ago, and for the behavior of building FHE in Web3, I believe we may be one of the most earlier to do this. Yeah, and actually our solution to enhance the security of AI and the POS network is we are using an FHE voting mechanism to help provide consensus, secured consensus to AI and POS networks.
Could we just double click on that? Because I'm sort of familiar with like EigenLayer, like you're able to use the benefits of the security of the Ethereum network, right? You're able to extend those security guarantees to other protocols with staking. How does FHE and Automata like fit in there?
Yeah, actually, we would build an FHE layer above them to provide extra security for the consensus. The idea of using voting to get consensus is actually we are enlightened by a project called BitTensor. They are using voting to get the consensus. They have miner, they have validator, they vote to get consensus. And the reason why we have to use voting to get the consensus of AI is that the consensus logic of AI network is quite different from the traditional blockchain. Because for traditional blockchain, they are ledgers of assets. So this means that for different nodes, they will generate exact same record for a specific transfer behavior. That's called transaction. And we just use simple hash matching to get the consensus. We use BRS signature aggregation to get the consensus and from all of these nodes. That's the consensus of traditional blockchain. However, in AI network, we cannot do this because no matter what you are doing of training, tuning, or evaluation, all these steps, they have randomness. This means if you have a specific task and you assign this to different nodes, and they won't generate the exact same result. So that's why we have to use the voting mechanism to get consensus, because in the voting mechanism we can do the computation, and we can have the customized consensus logic. So that's the reason we just build an FHE voting mechanism. And actually for voting, we have a token called VFHE to incentivize the voters, and they restake to get VFHE, and they vote to get more reward. Because of that, there is another problem introduced. Because the voters, they are incentivized. They have the motivation to get more benefits, even by cheating. They can simply copy the vote of others if we do not provide.
You answered my next question, which is why encryption and why FHE for this voting mechanism, and so this is why.
Yeah, this is why. Yeah, because if we do not provide extra credentiality for the blockchain, and the voters, they can get the vote of all the others, and they can copy each other's. In that scenario, that won't be a fair voting, because we know some of the voters, they are insiders, some of them are big whales, and they would be copied. And especially for AI networks, because in AI networks, it's about intelligence. For token assets, we cannot steal it by copying it, right? But for intelligence, we can copy it to steal it. So in that scenario, credentiality is quite important. So we use FHE to protect the vote. Actually, we encrypt the votes, and we will do the computation above the ciphertext, and then we get the result.
Fair and honest elections. That's what we're after here.
Fair voting. Yeah.
I would like to add a little bit more. Actually, it's more than that. I guess now the new hot thing is like AI, right? So like the use case is in AI. But this kind of like encrypted votes is also important to solve another problem, which is like the problem of the lazy validator or the lazy worker. I'm not sure if any one of you still remember, like back many years ago on back then Twitter, there were all this discussion on, hey, how can we make it such that like we can ensure that validators are indeed doing the work and not just like, hey, I saw that answer, I'm going to just think that I'm just going to copy the response from the first validator that submits, and that's it. And what is going to happen is that this whole scenario will actually devolve down a case where you only have one single validator doing the work. The rest would just be copying the very first validator that reviews it. So there's a lot of like schemes and like protocols that are being designed and talked about on how to solve this problem. Using encrypted kind of like voting is a very elegant way to actually solve this problem, because you submit your kind of like work, no one else can see it, you can aggregate it using FHE.
Yeah, you can't copy the answers of the smart kid in the class if you can't see his paper.
Yep.
Yeah, actually that's a very good point, because as we talked before, we have to cooperate between among the FHE, TE, ZK, because they actually cover certain area. For example, the FHE, it cannot cover integrity. Yeah. Just that point, because we cannot assume that the one who are doing the FHE computation, they just do the correct work. We don't know that, because all of them are in ciphertext. We do not know whether the node just do the computation in a correct way or just generate some random ciphertext. We don't know that. So we have to involve other technologies to make sure that all the nodes, they are doing this, in a correct way.
Keep them honest, right? Trust but verify.
Yeah.
I just
Yeah.
want to, if we have time.
We do, but we are running short. So, but yeah, please
Okay.
take us home.
So I just want to add, from looking at the performance side, that we noticed that from a high level, ZK and FHE actually share quite a lot of the same computational bottlenecks. So mainly, actually, but in both cases, is memory bound. It has been our experience. So on ZK, as we're going from a large field for example, the BLS, down to small fields, which is kind of the current wave, like SN31, we're entering the point where no matter how fast your computation engine is, you're still going to be memory bandwidth bound. And actually, it's the same with FHE, I believe.
Exactly, yes.
A trivial for everyone. Actually, we talk about FHE, MPC, ZK, all of this, right? ZK and MPC actually uses like partially homomorphic or fully homomorphic encryption. So like they are all related. We are all related. So we are one big family.
I like it. That's a perfect one to end on. So thank you so much, guys.
Thank you.
Thank you.